say a little bit about your background?
Sure. I've always been interested into biology and math. And so that led me in undergrad to study both of these fields. And then in grad school, I did a PhD in statistics with a concentration in statistical genetics, just because, I love the math, but I still want to do the applied side in biology. And so while in grad school, I did a lot of work on developing computational tools and methods, and the analysis of applying it to the genomic association analysis. And so when it was time for me to graduate, I still looked at opportunities within that field. And that led me to Regeneron, great team. While there, I got to really learn or have access to the wide, the large scale of the data that's there. Because in grad school, I was working in very small data sets. So it was really through this opportunity at Regeneron that I got to really understand the challenge that we're encountering now more and more with very large data sets, many cohorts, many number of phenotypes that are recorded for all of these cohorts, and also the number of the size of the genetic data, the number of variants as well. And so, yeah, it's been an experience.
Yeah, no, it's a fantastic cohort. I mean, it's always kind of a pleasure to see how big and how varied that cohort is. And Leland, would you mind kind of talking a little bit about kind of your background and kind of some of the work that your team does inside of the RGC?
Yeah, so I actually studied physics in graduate school, and before I joined the RGC, I worked in the nuclear power and industry and in defense for a little while. So completely different and absolutely nothing to do with pharmaceuticals or even biology, really. But I grew up in the 90s, which means I thought that Jurassic Park was the best movie ever made. And so I always had like a little bit of a charmed view of what genetics is and what it could be, but had never, when I learned biology, it was before 2000. So I mean, they really weren't even, the whole genome project hadn't even been completed yet. So I didn't really make the connection that like genetics is math at that time. But then just by serendipity, a few years ago, about 3 years ago, I happened to be taking a tour of the RGC at Regeneron, the main campus in Tarrytown, and listening to not just, I mean, the science and everything that they were doing at that time was amazing and just really impressive, but also the person giving the tour talked a lot about the data challenges they were having, the scale of the data, the speed with which it was coming off the sequencers, and started talking about some of the technologies that they were using to try to handle all that data. And I was like, well, I understood about half of the words that he used. Maybe I can apply for a job here because this sounds really cool. So that's how I joined the RGC and how I ended up working in this field. I think Joelle touched on the math as being really what drew her, or what she really loves about statistics. And there's a common trope. People often say math is the universal language. I don't really know exactly what is meant by that, but I do think it's true that a lot of different things, when you abstract away the details, the math looks quite similar. So it's been really fun to sort of just look back at some of the things I did in graduate school and my research after that, and had this applying a lot of those same mathematical principles and tools that we always use, just to a completely new area. It's been really exciting. My team at the RGC is in the bioinformatics, genome informatics, and data engineering is the full name of our team. And we have been trying to develop really invent from scratch a new way of managing a genomics data lake. I think prior to really the past few years, most people doing statistical genetics work tended to focus on one cohort at a time. The cohorts weren't that big. But at the RGC, we have this really unique problem that we have lots of different cohorts of varying different sizes, and we have to try to find some way of unifying all of that data together in a way that allows us to leverage the value of combining those data sets. So you could always analyze them separately, but you get a lot more out of the data if you can find a way to use it together. So that process of getting all this disparate data and harmonizing it and creating a robust data lake that all of it can go into and work together has been my team's main focus. And almost all of that work has been done in collaboration with Databricks using Apache Spark. A big part of that work has been developing the GLOW project, which we've done in collaboration with Frank's team at Databricks. And up to now, the focus of that work has been taking those genomics file formats that we're all familiar with, like the PVCF, BGen, those things, and leveraging the fact that with Parquet and Spark, we can actually create very rich hierarchical file formats and schema for those data. So it makes it a lot more natural to handle in some ways than the flat file and the flat text files. And that's been really powerful also in letting us leverage all of the very nice functions that are naturally built into Spark, not necessarily for genomics, but have really a lot of use in analyzing those large data sets.
Yeah, no, you know, I think it's been just kind of tremendously fascinating to see how the field has evolved. You know, for me, actually, back when I was in high school, I went to a summer camp, whereas, you know, it was like a tech summer camp, and I had to do, you know, I had to actually go ahead and do a gel. And I think at that point in time, I entirely swore off the idea of doing biology. I was like, this is so incredibly tedious. I will never do this. And I wound up going into semiconductors, which, like, oddly enough, like, you know, led into, you know, kind of doing, you know, originally some work in high throughput data acquisition for proteomics. And then I really went down the semiconductor route, went into wireless design, but wound up bubbling back up and going into genomics. And, you know, for me, when I was at Berkeley, you know, we were working on the Atom project. And like back in 2015, we were working on, you know, on reprocessing Simon's genome diversity data set with 300 whole genomes and reprocessing all of the RNA-seq data in TCGA. And, you know, we wound up with a data set of 20,000 RNA-seq samples. And at that time, you know, those data sets were unimaginably large. You know, I think, like, I was talking with some of the RGC folks recently who were saying, oh, you know, back then, you know, we were doing 20,000 exomes a year, and we thought that was, you know, that was enormous. And, you know, now you're up to, you know, multiple hundreds of thousands of exome sequence per year. So it's, you know, it's been kind of enormous to just see how the field has grown, and, you know, how kind of some of the translational applications of genetics are, you know, are really starting to grow. You know, I guess I'm actually kind of curious, you know, to hear a little bit, you know, both from, you know, Leland and Joelle, you know, about kind of the balance between, you know, some of the data engineering work and some of the mathematical and statistical work inside of the RGC. You know, how does that collaboration work? And, you know, over time, as the data sets have grown, the number of cohorts has changed. You know, what is kind of some of that back and forth between, you know, your two teams? You know, what does it look like, both in terms of getting the data sets prepared, collaborating on methods? What have you seen there?
So from our side, like data engineering side, for the most part, that collaboration stems from statistical geneticists or analysts who have some tool that they're familiar with that they really like, or some analysis that they have traditionally done, that as the data has grown, it suddenly becomes something that, you know, when they used to do it on their smaller data sets, it would take an hour maybe, and then at some point it grew to be a day, and then a new cohort comes out that's really huge, and they sort of try to extrapolate how long that analysis is going to take, and they realize it's going to take, you know, 2 weeks of a computer running full time to crunch through all of it. And then that's usually when a conversation starts with us, where we try to find some way of engineering a distributed solution rather than like a single machine solution that allow us to do that same analysis, but in a fraction of the time, or in a way that will scale sort of infinitely as the data sets grow, so that we don't get in this situation where there's an essential analysis that has to be done, and that's just not possible because we've always done it in the past and it's worked on small data, and now we have a data set that's too large. So that's a problem we want to avoid, sort of head off before we get to it. So that's usually our role, is developing methods of doing those analyses using Databricks, usually Spark for the most part, doing and like a distributed version of existing algorithms.
Yeah, it makes a ton of sense. And, I think, one of the great definitions that I've, kind of tongue-in-cheek definitions that I've heard for, when you're working with big data is when, algorithms that linearly scale become a really big problem. And, especially you look in the RGC and, just in terms of the growth of exomes per year, you're very much so in an exponential setting. Joelle, I'm kind of curious, to hear kind of from your perspective, as a statistical geneticist, what are some of the kind of, common challenges that you're facing, both from a method scalability as well as, just kind of a workflow challenge in working with this many cohorts and data of, that's really hitting the million samples range?
So I want to touch back on what we didn't mention earlier with like going back to just the format of the files. That's already like a challenge in itself. There are some tools that work with a specific format and some tools that don't work. And so when you think of, if you have, let's say 1,000 sample, it's not that computationally burdensome to do those conversions. But when you're talking about on the scale of 100 of thousands of sample, that becomes, let's say, a concern. And so there's already like that aspect. And then just as far as the structure of the data sets, there are some data sets that require more statistical care, let's say, as far as what analysis can be done. And that's a big component of how we worked on developing the Regeneron method to be able to analyze a fairly wide variety of phenotypes, and yeah, just managing. And there's like many different sources. There's not just the genetic data, there's the phenotypic data that you also have, and covariates and so on. So it's it's a growing skill, let's say, to manage.
Yeah, no, I think that makes a lot of sense. And, I guess I'm kind of curious for you, like when you looked at some of those data sets and you had, these, I think a lot of the, a lot of what we find in, any sort of large scale statistical processing, any sort of large scale ML, kind of data set conditioning, appropriate statistical conditioning of your data is a really big problem. I'm kind of curious, what did you see that, that provided insight into that problem? Like, what were there specific things about this data set that these data sets that kind of stood out? I know there's a large body of work in StatGen on on kind of questionably conditioned phenotypes, but I'd love to hear a bit more from your side.
I mean, a major issue in genetic association studies is confounding, and so I mean, there are tools to it. For example, one major source of confounding is relatedness, right? So when you have people from, let's say, the same family in your study, and you have many of those families together, and you do have to take that into consideration. Another source, for example, is when you're sampling, let's say, all across Europe, let's say, and there may be some different, let's say, genetic properties in all of these different parts. And so so it's little, I shouldn't say little, but it's important features of the data that you do have to take into account.
Yeah, it makes a ton of sense. I mean, especially, I know so many of the populations that are fruitful, kind of from a biomedical purpose, especially from a, target identification purpose, are populations that have some sort of, interesting intrinsic structure. I mean, I was chatting yesterday with a person that I work with who's in an organization where they're running a genome sequencing project for a, kind of a geographical region that has lots of small islands, lots of kind of, valleys that are deeply separated. It has kind of a founder population. It actually has two founder populations that for, kind of a variety of different social factors did not intermix. So they're doing this project and they're having to deal with all sorts of unusual kind of, genetic confounders and, constraints around relatedness. And, I think that's kind of what led to the development of kind of the Regini kind of genome-wide regression model, correct?
Exactly. There was, and so when I joined RGC, Leland and other members of the team had done amazing work looking at quantitative phenotypes and trying to build a method that would encompass the whole controlling for genetic confounders, but also just handling the scale at which the data was growing. So which was becoming a bottleneck. And so, yeah, so they had done amazing work at that. And then, like once we had the groundwork laid out for just quantitative phenotypes, then we thought, okay, let's extend it because you have many of the features that are collected on people that are actually more like disease-based, like case control status for some sort of disease. And so then we did this extension to more on the binary side. And we just, so I mean, from a statistical point of view, for me as a statistician, I love it because there are just a lot of opportunities for expansion of this whole genome regression idea.
Yeah, definitely. I think one of the things that's been very interesting, for me, just kind of to touch on the performance side for a bit, we've been collaborating on Glow as a software tool for a while, and there's a lot of really interesting tooling in Glow that takes traditional single node bioinformatics algorithms and scales them out so they can run in a distributed fashion. But one of the things that I really like with the WGR implementation in Glow is that it really goes ahead and linearly scales out. It is not quite embarrassingly parallel, but very close to a truly embarrassingly parallel algorithm. And Leland, would you mind kind of diving into that a bit? I know there's been kind of a lot of discussion about tools like Bolt, tools like Sage, and kind of the challenge with fitting that initial genome-wide model. Yeah, how did you kind of think about building this out, and what were kind of the architectural and kind of mathematical principles that led you down the initial design?
Yeah, so as you referenced Bolt, there are existing whole genome regression, or basically methods that use a whole genome regression to try to account for the genetic confounders that Joelle was mentioning. Bolt and Sage are probably the standards for the most part for most population level, like large population-based cohorts. And they both have really nice scaling properties, but they are both single machine methods. So, and they're both one trait at a time. And so that it's not too burdensome if you have like one data set, say one cohort and a handful of phenotypes that you want to analyze. But at the RGC, when we've got dozens of cohorts and each one has hundreds or thousands or tens of thousands of phenotypes, we've felt that there was some room for trying to at least get that to scale beyond a single machine. You end up in a point where, in a situation where it's easy to distribute the association testing part. If you just forget about the whole genome regression for a second, that's a relatively easy problem to parallelize. But so in terms of wall clock time, that doesn't end up being a bottleneck. But then there's really nothing you can do to try to speed up the wall clock time of the whole genome regression method. So, or the whole genome regression portion of those methods. So we wanted to
Bolt and Sage, right?
Yeah, Bolt and Sage. So first of all, we wanted to build something that could parallelize across multiple machines. We wanted it to be able to analyze multiple phenotypes in one go, rather than, or at least for as much of the math as possible, we wanted to be able to make it so that it would be able to analyze multiple phenotypes at once. And then also we wanted it to have a clean separation from the actual whole genome-wide association test step, so that you can sort of use it to in ways that after when we built it, we thought that we would probably use it in ways that we hadn't foreseen. Like Joelle was mentioning, we built it for quantitative traits, and the same principles allowed us to extend certain parts of it to binary traits. And in the future, we'll be able to extend it to different types of survival analysis, for example, or other phenotypes that are not just the standard quantitative or binary. And that clean separation of the whole genome regression from the actual association testing will allow us to do a lot of those extensions. And so as far as trying to engineer the method so that it would be distributable and parallelizable across as many machines as we wanted to throw at it, the main driving principle was that we wanted to ensure that for any particular task, only a fixed piece, a chunk of the data of fixed size is required. So for example, just very simplistically or naively stating it, really all we're trying to do is fit a linear model where the design matrix is samples, individual people are rows, and then columns are genotypes. And that matrix is big, and it's big, and it's also doesn't really conform to the nice shapes that there are tailor-made algorithms for. Like there are special algorithms for very tall, skinny matrices. There are algorithms for very wide, short matrices, but this matrix is pretty much square.
And and what's kind of interesting as well, like for me, coming from the semiconductor side, I'm used to dealing with very big, very large square matrices that have very high sparsity, which is also, something that you see with, especially with NGS data. You all are dealing a lot with exome data. Yeah. And, it can be very highly sparse. We can, in some data sets, see, like a 10% of the matrix populated or less. But it doesn't even have any nice sparsity patterns. So it's, it's kind of an additional challenge.
Right. Yeah. So in looking at this, we realized if we wanted this to be parallelizable, we had to find a method that would not require the entire matrix to be in memory on any single machine at any given single time. So we basically just blocked it up into, we knew we wanted to make the method based on a block matrix structure. And so we just, at every step in the process, we made sure that however we decided to attack the problem of doing the transpose or matrix inversions, that at no point did we need to have the entire matrix or even an entire subset of the columns, say, in memory at a time. So, and the outcome of that is that as the data grows in either the number of columns or the number of rows, we can accommodate that by just adding more blocks of those constant size, so that the matrix block size stays constant, and that will let us guarantee scaling to however many samples and however many variants we ever might want to accommodate.
Yeah, makes a ton of sense. Makes a ton of sense. So, ultimately, you've essentially got this blocked matrix way to go ahead and calculate, some genome-wide terms that essentially wind up creating a calibration for the phenotype on the basis of of this genome-wide regression, right?
Yeah, that's essentially, you're just trying to say trying to explain as much of the variance of the phenotype as you can based on this large genetic data set. And we call it genome-wide, but we don't include like the entire genome in there. It's usually around 500,000 or so common sites that you can sort of use to find people who are genetically similar to each other. And so it's a correlation with the phenotype. We're not necessarily with this step, trying to find the regions in the genome that actually cause or have some kind of functional purpose. It's really just a correlation.
Makes a ton of sense. Makes a ton of sense. And one thing that I think is kind of interesting with this is, ultimately, even though you all are using a very different implementation, of kind of calculating this genome-wide correlation, you've been able to achieve very similar accuracy to methods like Bolt and like Sage. What was kind of, was there anything that was kind of critical in terms of building the method to go ahead and achieve this? Would you mind like kind of telling me a bit about, kind of that ultimate process of, getting the results to match? Like, was that a goal? Was that something that, just kind of joyously happened during the process?
Yeah, so this is something that Joelle deserves a ton of credit for, because the most essential thing that has really accelerated the development and allowed us to make good progress was establishing a really clean benchmark data set that she put a lot of thought into filtering sites, filtering samples, and she found some really interesting situations where you had variants that were strongly correlated with each other across chromosomes, which is, there's a couple of reasons it could happen, but you never really want it to happen. So for this design matrix, so she was able to find those and filter all those out. And it basically just remove all the questions of like, are we really making apples to apples comparisons with Bolt and Sage? So once that data set was established, we could just run Bolt, run Sage on those data sets, and then know that we could take exactly the same data and run Regini on it, or the GloWGR method on it, and know that we're making the right comparison. And then as far as making those comparisons with Bolt and Sage, we kind of knew like Regini has a ton of really attractive performance aspects compared to Bolt and Sage, but ultimately people would not be super excited to use it if it wasn't at least as good as those methods in terms of the test statistics that you get out of it. So that was because they are the industry standard right now. We knew that we needed to compare well with them, which is why we focused on those. And Joelle probably has a more nuanced and better understanding of those comparisons than I do, but that's my perspective anyway.
Yeah, I totally agree with what Leland said. It was, we did want the Regini method to be comparable to the other methods. And for example, with the binary trait, there was this whole this important case when the trait is very rare, you can get inflation. So you can get very significant results that are actually false positives. And so this was a situation we also have to think about, because in Sage, they do have a method that accounts for that. And so we had to put a lot more thought into the statistics as to what we could use to tackle like that issue. So,
yeah, that makes a ton of sense. I mean, especially, when I think about a lot of these biobank scale data sets, they're interesting in the sense that you do actually get many of these traits that are relatively rare in the population overall. And they're a very powerful tool for kind of diving in and understanding those sorts of traits, those sorts of divergent biomarkers much better. I'd love to kind of hear a bit more. For me, I've always been kind of interested in the benchmarking space. Back when we were at Berkeley, my advisor David Patterson, he's a really strong, deeply held believer in the necessity of benchmarking. And some members on our team went ahead and built a benchmark for variant calling back in 2013 called SMASH. And then there's been a lot of evolution, especially in the variant identification side, through Precision FDA, through the DREAM challenges, on coming up with good genomic data sets that allow us to benchmark variant calling methods or gene expression methods. But you haven't actually seen quite that much, as much work, as sophisticated of work in the large-scale genomic variation space. And I think that's been just kind of a bit of a challenge that people are facing as they go ahead and benchmark these methods and try to characterize them a bit better. Would you mind kind of talking about, kind of how you went ahead and did that benchmarking, and what are some of the lessons learned from that process?
I mean, the key aspect that we wanted to do was just make sure that for all the methods, what went into one method was exactly the same across all the methods. And then we had to think about what measures were we needed to track of, and one of them obviously was the computational time. One of them was the memory usage, because so there had been several methods proposed recently that were very memory efficient and computationally fast, and so. And then we also wanted to look at just the test statistics, the output from those. And so it was right. So once we knew what we actually wanted to benchmark, then just making sure that everything, getting all the same files, the same files that would be used in all the different methods. So obviously some methods have. So there was one method that had a different format, but then you kind of account for, you just take out the time it takes to convert to the format. But yeah.
No, it makes a ton of sense. Makes a ton of sense. And for what it's worth, on my side of I've seen a number of bioinformatics papers in the last few years that have prided themselves on tuning their memory footprint. And as a former, embedded systems person working on, chips that would go into cell phones, I'm like, I'll take however much memory is on the machine. Memory optimization is not something I'm going to do, but I digress.
Right. But it does become an issue when you have a lot of samples, and then
definitely
that really dense matrix that, yeah.
Well, I think actually, like especially, in some of the work on the, in processing multiple phenotypes at a time, I think that became a big issue, right? Because, one of the big advances that you ultimately achieved was you were able to process many phenotypes in a single batch. And I know with some of the other, tools that we've worked with and we've collaborated with people on in the past, they've been limited to processing 10 to 20 phenotypes at a time, or sometimes even locked to a single one. Whereas obviously, the data sets that, many of us aspire to work on, UK Biobank, if you work on that naively, you have 5,000 to 20,000 phenotypes that you can start with. So I imagine that was kind of a big challenge.
Mm-hmm.
And, I guess I'm kind of curious, for, especially for you all, some of the work you did in, especially in Regini, and that now has been kind of flowing back to GloWGR. What did it take to take this quantitative trait, this quantitative trait method and apply it to binary traits? What kind of sorts of changes did you have to make? Was it a straightforward process to kind of make that evolution and kind of broaden the method out?
So the main drawback when you switch from quantitative to binary is that as far as the method, so the most logical method to use going from linear regression is just to do logistic regression. But the main drawback with logistic regression is that it's more computationally intensive than the linear. And so we knew, because and the whole genome regression step, the first step of the method, that so for quantitative traits, you have 2 steps of linear regression. And so we, you may think that, okay, let's just replace that with 2 steps of logistic regression. But then our thought was that because logistic regression is more computationally expensive, so let's try to see if we can just first do linear regression and then switch to logistic regression. And it was really an idea at first, and then through applying it, we actually saw that the results came out. It worked really well, and so that was like for the first step. And then for the testing part, like I mentioned before, because with binary traits you have this. When you have a rare binary trait, you kind of have to be careful about how you build your test. And so that was on the testing side, the main focus for us, because tests for logistic regression are pretty standard, but it was just adding in some sort of correction for the rare binary traits, which, as you said, there are many of them, and let's say like the UK Biobank and other data sets.
Yeah, makes a ton of sense. Makes a ton of sense. In you know, I think intuitively, it does make some sense that the kind of taking the first step of the GLOWGR, that computes, or the whole genome method that computes on the blocks matrices and keeping that as linear. That does make sense. We've actually seen people in the past that have even run a linear regression on a binary trait, just to go ahead and essentially as a first pass to stratify out all of the variants that are extremely unlikely to be associated with a pass or with a trait, so that they can then go back and run a second path for logistic regression. I neither advocate for nor against this process. I'm just saying I've seen people do it. Yeah, it's definitely kind of interesting to kind of see how that method is worked from a performance side. And I think it makes a lot of sense. I guess I'm kind of curious, for the, especially for dealing with some of the, the rare and highly imbalanced binary traits, when you look at, some of the various different regression methods, be it Firth, be it using kind of like a saddle point approximation, I know there was some thought that went into kind of accommodating that. How do methods like that tie in with the whole genome regression approach that you had used?
Mm-hmm. So in the whole, so the goal, one goal of the first step is not only to control for genetic confounders, but it's also to capture the background polygenic effects. So if you think of in step 2, you're just looking at one site, you actually gain more power if you can condition on like what's outside of that site. And so having that step 1, building those like that polygenic prediction, like for like the background effects, actually can help you a lot in step 2. And so that was a separate component from the actual testing and making sure that our test was calibrated, where, like you mentioned, so we did look at what other methods we're doing to account for imbalance in the trait, and like Sage, which you said, the saddle point approximation. We also looked at just in statistical papers, and then the first correction also came up, and so we decided that it would be really cool to also implement that, because people are interested into the statistical test part, but they're also interested into getting effect sizes, and so with Firth we are able to get those corrected estimates.
Yeah, Joelle has lots of really audacious ideas that end up working really well. One of them was on the Firth method. People have liked it and used it for a very long time, but it's really pretty computationally intensive if you want to test every site with the standard Firth the Firth method. And she came up with an approximate method that if you're sort of careful in doing all of the work that you possibly can, that you don't need to repeat at every single site, and you do that in a way that is consistent, you can reduce the computational burden of doing that Firth test really substantially. And that's like, we focus a lot on the whole genome regression part, but Joelle's approximate Firth test, I think, is a really huge part of Regini and is going to be, I think, pretty transformative. I think it was recently even just ported over into Plink now. So I think people have immediately seen the value of that fast Firth test. And
that's awesome.
Joelle mentioned the
you really know your method has made it if Plink goes ahead and picks it up. So
yeah, and the effect size was a big part of the decision to include Firth in Regini. As Joelle mentioned, Sage uses the saddle point approximation, which gives really good test statistics, but you don't get a reliable effect estimate. So you don't, in terms of like how strong or what direction the effect of that particular SNP is going relative to the phenotype. So Firth allows you to do both of those things. You get a good test statistic and also a reliable effect estimate.
Yeah, makes sense. And just kind of out of curiosity, how does the, I can imagine on my end, but, especially like on the statistical and the analytical genetic side, how does that effect size kind of come into play? And, how does that kind of combine with all the other different measures that you're, between the test statistics, the effect size, and other things that you're collecting? Like, how does that ultimately give you a better, more holistic picture of the trait?
So we have some members of our teams who are who carry more often meta-analyses. And so in these meta-analyses, you do use effect sizes. And so that's where you want to have something that's well calibrated and a reliable estimate. We've seen that with the saddle point, you can get estimates that are 2 orders of magnitude off. So it
seems like a possible issue. Yeah.
Right.
I was going to say I am a deep believer in approximate methods, as long as they ultimately give you results that are accurate enough. And 2 orders of magnitude seems like a possible challenge from an accuracy side. So yeah, I guess I'm kind of curious. Leland, you mentioned audacious ideas a minute ago, and I know earlier on, I think one theme that's come up a lot is how the whole genome regression model ultimately gives a polygenic score, effectively a polygenic calibration. We talked a bit about kind of extending this to, to survival modeling. And I know, for us, we've done some work recently, with some other folks on top of UK Biobank, where they've ultimately use GWAS hits combined with survival methods to get a better understanding of, kind of the genetic burden of disease. What's kind of coming up next? What are the next big audacious ideas?
There are actually, it's pretty ironic, but at first we started this, and at least in my mind, I thought I really concentrate on step 1 being the bottleneck. But now that we've pretty well addressed the step 1 issue, now step 2 is becoming a bottleneck in the sense of there are just a lot of things to test. And so that's why, having a platform with Glow, you can just like run things across many machines, but on the Regene side, for the user with their single machine, that's becoming computationally challenging. And so we are thinking, and like you mentioned with, for example, with exome data, where you have matrices that are very sparse. So one thing that we've been thinking of is incorporating that into how we store the data and how we even like bring it into the test to use like the sparsity of the data. We have been thinking, and a lot of the extensions that we're thinking is for step 2, for example, you could have multivariate tests, interaction tests. There's just a wide range of statistical methods that could be applied at that level.
It
makes a ton of sense. Sorry, go ahead, Leland.
For anyone who, if for some reason you haven't read Joelle's Regine paper preprint, first you should go do that, first of all. Second of all, just so we're on the same, when Joelle's talking about step 1 and step 2, step 1 is the whole genome regression step, and then step 2 is the actual SNP by SNP association testing. And so one of the really powerful advances, and it's in retrospect, it's a little bit obvious to do this, but a lot of the best ideas are obvious in retrospect. The clean separation of that step 1 whole genome regression from the association testing will prove to be extremely powerful. And that is what has led to this just like multiplication of ideas that Joelle is talking about. Now, because of the way this method separates those 2 things, it sort of sky's the limit in terms of the types of things that you might go now and test, and versus something like Bolt or Sage, where those 2, the step 1 and step 2 are really tightly coupled, and it makes it hard to extend the whole genome regression part.
Yeah, and it's kind of it's kind of a nice glamorous separation, because ultimately you're essentially able to use step 1 to calculate a calibration to the phenotype, and then that resulting new calibrated Y hat phenotype can be, can be used with any downstream test that you want. So you're not, you're not locked into whatever comes in your standard regression package. You can truly extend it anywhere.
Mhm.
I guess I'm kind of curious, with you, like when you talk about some of the things in the like in the survival kind of survival analysis space, is it, like what would that kind of, how would that like play in? Would that be something that you would run on top of the like with calibrated phenotypes from step 1? Would it be an extension of step 2? What, like how would you see that playing out?
So survival data is pretty unique in the sense that you have both a quantitative phenotype and a binary, you can think of it as a binary phenotype, which indicates the censoring. And we are looking in, so we are actually actively working on this. And similar to how we extended from quantitative to binary, where we have that, where we did this compromise between linear and logistic and didn't just do a full logistic regression. Just because, the linear model is the simplest type of model to fit computationally. So here we're also thinking of, and a similar idea. The standard model and survival analysis is the Cox, a standard model that you use is the Cox proportional hazards model. And so we are, we're thinking at the first step of this whole genome regression, how to incorporate that so we can use both. So we don't have to choose just the quantitative phenotype or just the binary one. We actually want to have as much power as we can to capture all those like genome-wide effects.
Makes a ton of sense. And I know it's, I think one of the things that's kind of interesting with survival data as well is in some settings, it does have maybe a little bit worse of a missing data problem than, at least I've found this in the past, like when we were working with oncology data, some of the oncology data that we had from TCGA and others had a little bit more of a missing data problem. That's probably kind of more of a broad epidemiological and kind of misdiagnosis question. So I digress there, but it's definitely a fruitful area with lots of needs. And I guess Leland, from your side, especially like when you think about some of the work that's been done in GLOW on the GloWGR method, do you see kind of places to go ahead and extend further? I know we've been talking about kind of improving the performance of some of the downstream step 2, per variant tests, but would love to kind of get a bit of your perspective.
Yeah, so the big push right now on the GLOW side from us is wrapping up the binary traits. So right now, GloWGR has the whole genome regression implemented for quantitative traits. We're really close to having it, the logistic regression implemented to address binary traits. Hopefully that'll be available as a part of the GLOW by the end of this month. That's my hope. And after that, something else we've been working on is adopting some of the really good ideas that are in Regini about how you can best optimize doing the association testing by doing basically batches of tests at once rather than doing single tests at a time. So doing as many of the operations with matrices and then letting a nice linear algebra package like NumPy or Eigen in the case of Regini handle optimizing, doing those things rather than trying to do it ourselves. We've seen a lot of promising results there in the Databricks using and in Spark using the basically using the pandas UDFs to do a lot of that work. And it's been actually going back and then comparing with Regini in terms of performance. Like we're getting, it's almost spooky. Like you look at the line of if you imagine a plot of, I'll do it this way so it's facing, no, here we go. The y-axis is wall time and the x-axis is number of cores. Regini is a single machine method, but you can run it on multiple cores. So the upper left-hand part of the plot is sort of the Regini line. And if you imagine it's a log-log scale, so it's linear scaling is basically a line with number of cores. And it's like almost continuous now with the Spark version. So like by adopting some of the same approaches and tricks that are in Regini, even though they're completely different programming languages, completely different backends, that we're getting almost perfect scaling with what is going on in Regini. So I think at some point a flop costs what a flop costs. So that I think that is a good indication that in neither place are we paying a lot for overhead, and so that's really.
Well, and, you know, it's I think that's kind of a great note to end on, because, you know, one of the common misconceptions that people have when they go and scale out across many nodes is that, you know, in exchange for better CPU throughput, you know, being able to run on more cores at once, you know, they'll pay some sort of a performance overhead. But, you know, with kind of delegating to a lot of the optimized linear algebra packages, using a kind of well-tuned processing system. And I mean, it's amazing how fast, you know, Python and, you know, especially the NumPy ecosystem has gotten. 10 years ago, you know, I feel like nobody would have thought about seriously writing heavy-duty computational packages in Python. And now it's an amazing ecosystem for doing it. And, you know, ultimately, I think, you know, that's kind of the great power of open source software. You get a bunch of people working together on cool ideas. You see this tremendous collaboration across the ecosystem. And then, you ultimately get fun packages where, you know, for instance, in Glow, you know, we're able to take the awesome innovations around GloWGR from, you know, the kind of work on both Glow and the Regini method. We're able to use Spark to parallelize it out across many nodes. Spark efficiently delegates down to NumPy for some of the high performance linear algebra. And, ultimately it's really all the open source ecosystem coming together into one tool. So, again, realize, we're out of time for today. Thank you both very much, Joelle and Leland, for your time today. It was a pleasure to kind of talk through this some more and to hear a bit more about the background and some of the exciting next steps. So thank you very much for joining us. Thank you very much to the members of the audience for going ahead and signing in and joining today. And we will catch you sometime early next month with the next installment in the Glow Tech Talk series. So thank you all very much for your time today. Take care.
Thank you, Frank.
Thank you.
Our pleasure was mine.
Bye, guys.
Take care.
Bye.